Seb, thank you for the introduction. So my role at dSPACE is being a product manager for the sensor simulation. And today's session, well, as Seb already said, is within the simulation stream. So simulation in terms of serious simulation. So this is not like FIFA is like a football simulation or any kind of racing games, which are racing simulations. No, we cannot give this to any kind of online gaming shops. We would like review bomb there. Gameplay sucks and no sound available. So this is something different. So this is not directly for your joy or so for playing it. But what you can expect over here is we will talk about autonomous driving, and there are actually different levels of autonomous driving, right? So I will give you an introduction to that, and also to the challenges for autonomous driving. I mean, this is not something which is currently on the road right now. And we've built a solution which is utilizing the Unreal Engine to solve at least one or maybe two or three challenges for autonomous driving. And so actually, everybody of us is spending a lot of time in the car, right? And according to the AAA, the average American spends 12,000 miles per year in the car. So these are actually two round trips between San Francisco and Washington, D.C., right? So this is a lot amount of time. And this is basically like 50 minutes per day in average. So, benefits of autonomous driving. So what would you do with those additional 50 minutes, right? You could watch a new TV episode from your favorite show. You could take a nap on the way to the work to get there better rested. Maybe you are too tired to get home from a party. Gaming, well, I would do definitely play some games on my mobile phone, and there are even more countless activities you could do in the car, right? But do you know which one of those is my favorite? Actually, none of these. So there's an issue. And this issue is that we are having a lot of fatalities, a lot of car accidents all over the whole world, right? And do you have a feeling how many people are dying every year? So let's look at this plot. So on the x-axis, you can see the year. On the y-axis, you can see how many people have died according to the NHTSA. And you can see that, we were right about 45,000 fatalities per year in the US, right? And something happened. Something happened between 2007 and 2008. And this was actually technology, okay? Technology came there, a driver assistance system, the electronic stability control, for example. The ESC, in short, is just checking if the car is oversteering or understeering, and it helps you driving the car. And you can see that a third of the fatalities were reduced back then, right? So what do you expect in the next years? I mean, a lot of different additional driver assistance systems arrive there, like blind spots detection and like a forward collision warning, for example. Well, it stayed like constant for 5 years, and afterwards, the trend was going up, unfortunately. And this isn't great at all. I mean, as you can see, in the last year, 2021, we were on the highest level since 2005. And you know what? This is due to human errors, because people tend to go for speeding. People are not buckling up in their car, right? And there are fatalities again on the road, way too many fatalities at the end of the day. And let's have a goal, a common goal, which is remove the steering wheel. You know what? Because mankind always finds a way around to circumvent technology, to harm themselves, and even worse, they are also a hazard to other people, right? And this is an issue. This is a big issue. So let's remove the steering wheel. And actually, there's a plan for that. Yeah? So let's have a look on the roadmap how we can achieve this goal. There are, according to the SAE, different autonomous driving levels, actually. Level 1. Level 1 of autonomous driving is feet off. Yeah, this is the word of driver assistance system. So the vehicle itself is still controlled by you, by the driver, but it is helping you, for example, to accelerate the car or to hit the brakes for you. This is level 1. Level 2 is the partial automation. Let's call this hands-off. So this means the car itself is capable of accelerating the car. It can brake the car, but it can also control the steering wheel, so to say. It can center your car in your lane. This is hands-off. But actually, the car constantly checks if you're putting your hands on the steering wheel. And if you don't, those driver assistance systems simply will disable themselves. Level 3, conditional automation. Let's call this eyes off. So this is something new. This is something new because the car is responsible. The car manufacturer is liable when something happens, when those kinds of automation is enabled, right? So basically, the car is controlling itself, but there's one thing, if the car is not feeling comfortable anymore, so to say, it will warn you. And you're having like 10 seconds or something to take over control of the car again. So this means that due to regulations, those cars have in-cabin monitoring. This means the car always checks your status to see if you're sleeping or something, and it will warn you. But you are able and you are allowed to use your mobile phone, for example, in level 3. Yeah, until then, level 1 and level 2, the driver was responsible. Right now, the car is responsible. And level 4 is brain off. And that is a cool thing because a lot of drivers already achieved this level, brain off. But unfortunately, their cars did not, right? And this is an issue at the end of the day. But this means you can relax. You can just relax, you can sleep in such a car, because these cars with level 4 automation are at any given time possible, where it's possible to control the car and even to create some kind of safe driving maneuver. They would just like hit the brakes, change the lanes, and stop the car for you. Typically, this is a local driverless taxi, so it's somehow geofenced. Level 5 is full automation, right? And this is probably what most of the people are somehow expecting from autonomous driving. So you simply put it in, like, get me to San Francisco, you're sleeping, and you get there arrested. This is level 5, actually, fully driverless. Okay, but where are we right now? Do you know that? I mean, no level 1, it is way too easy. No level 5, because, oh God, we are so far away from level 5. So let's have a look at level 2, 3, and 4. Level 2, this is something what is available right now. So you can buy almost every single car with such kind of automation. Level 3 is something new. This will actually come in the next year. Mercedes is actually the first car manufacturer who is selling cars which are able to drive in level 3, and they will start activating the service at the beginning of the next year due to EU regulations. But this is limited, okay? So within the Mercedes S-Class, you can go on a highway and it will regulate the speed up to 60 kilometers per hour for you, and only under specific conditions, like it is sunny and don't know about the moon somewhere, or there are regulations, but I think there will be updates also to this system to enable it even drive faster than just the 60 kilometers per hour. And at the current stage, they are not allowed to go to drive in level 3 in the US. So there are regulations currently which are missing in the US, but I also expect this, to change soon. Level 4 is in a somehow experiment stage, so to say. There are companies around like Waymo, like Cruise, who are having those local driverless taxis, for example, in San Francisco or in Phoenix. But there are just a few of them, and there are still issues. Don't get me wrong, this is amazing technology. They are doing amazing things, but this is just like, let's call it an experiment. So like a small sum up, how can you remind yourself what are those different levels? Well, basically from toes to head, right? You're having feet off, hands off, eyes off, brain off, and the robotaxi. So, but do you know how such an autonomous driving car works? So maybe we can compare it. We can compare it to you as a driver. So basically, when you as a human are driving a car, there are 3 different challenges, right? The first one is sense. Sense means you're using your eyes, you're using your ears to check what is happening on the road, what is happening in front of you. Are there pedestrians? Are there any kind of hazards on the road? What do I have to do? It is just like seeing, interacting. And an autonomous driving car has sensors on it, a lot of sensors like camera, radar, and LiDAR to interact with the environment and to get a good feeling what is happening over there. And from there on, the next step is think. This is also what you as a driver have to do. I mean, you're having your sensors, your ears, your eyes, and from there on you have to create like a motion plan. What are you trying to do right now in order to get, well, home safely, for example? An autonomous driving car has a challenge because it has different sensors, camera, radar, and LiDAR, and each and every sensor has another format, another output actually, right? So what you can see over here is just like an RGB image, just like a camera image, but a LiDAR sensor, for example, creates a point cloud, right? And you try to get a common understanding of the environment by merging all this data. And this is actually a challenge. And this is why typically you do a sensor fusion. And you're doing the sensor fusion, for example, on object list. So you're trying to get an abstracted view from your sensor data. So this is an example for the camera. Again, you're going from the left to the right to get this abstracted view, like driving shoe boxes or something, and you're interested in their position, rotation, and relative velocity compared to you. And if you're creating such kind of object lists, then it is very easy to merge the data from your different sensors. And from there on, the next step, of course, is motion planning, even for the car. And it is using different actuators to control the car, right? The steering wheels, the brake, the acceleration, just like you would, okay? So it looks like there is already a plan. The architecture is clear. So what is the challenge right now? Why don't we see any kind of level 5 cars around? So at the current stage, we are in the transition from level 2 to level 3. So this means the functionality is way more complex than before because the car is liable for everything it does. And there are new challenges on the roads, and you are not even aware about any risk, about any corner case, which might happen, right? And you got a lot of sensors, and you have to test them, right? And you're having different perception algorithms which are trying to identify objects and classify objects, and you're having developers, and the developers are pushing code like every single day to further improve the algorithms, and you have to test over and over again your different driving scenarios. So this means you have to drive millions of test kilometers, right, to test your autonomous driving. And this is actually where simulation kicks in, right? You need simulation to really test out your autonomous driving function. And this is why we've built Aurelion. This is a small demonstration, so you can see this is like a highway scenario over here. We are driving around. We are changing the environment, the weather, it is raining. You can see right now that, yeah, raindrops. We can, of course, also drive around in an urban area, make it foggy, snow. You can change the environment, right? You are building your road network, you can change the environment, and of course you can simulate sensors. So that was LiDAR, this is a radar sensor, this is a camera sensor with a fisheye view, ground truth information. So actually there's a lot you have to do in order, well, to give out, to have a solution for autonomous vehicles. And they are not just cars, right? Also agriculture. Is there something which needs this kind of sensor simulation? So Aurelion in a nutshell. So this means we are providing a solution which is capable of generating raw sensor data for different sensors, for camera, radar, LiDAR, soon to come ultrasonic. And everything can also be calculated in real time because our customers are having different use cases and different tests. For example, software in the loop. In this case, the whole perception and everything is calculated on a PC. But they're also having hardware in a loop test. In a hardware in a loop test, you're having like a high performance computer, which is integrated into the final car. And in this case, you're having hard real-time constraints, right? This means, for example, you're having a camera. This camera has an update rate of 30 Hertz. This means that you have to satisfy these constraints. Not faster, not slower, because otherwise it will go into an error state. We will simply say, well, this is not what I'm expecting, test is over. Yes, and of course we are also supporting 3D environment generation, which can also be modified by our users. So at the end, simulation is key. We are having new challenges due to autonomous driving, and simulation is how we can solve them. If you're wondering who's dSPACE, we never saw them in the Epic Game Store. Well, yeah, actually we are no new company. We are actually available since more than 30 years, and we are having like 2,000 employees at dSPACE. Obviously, I'm one of them. And we are having local dSPACE companies in like 6 countries, and of course also in the US, in Motor City, Detroit, and San Francisco. We're having solutions more than just Aurelion. We are also creating hardware, like hardware in the loop simulators. We are also having different simulation models for traffic, for vehicle dynamics. And our customers are from different industries like automotive, off-highway, aerospace, and medical engineering. And when speaking about automotive, those were our top 20 customers in the year 2020. You can see, yeah, there are a lot of different names on it, OEMs, but also there are tier 1 suppliers. But I would like to briefly introduce you to the sensor simulation history. So where does this come from, right? Actually, I brought a small video here, and I mean, we are having models in Simulink actually for vehicle dynamics since like 30 years or something. And we also developed a solution based on Open Scene Graph. Well, I guess some of you maybe know Open Scene Graph, hopefully, right? Yeah, great. So we had this a tool which was called, or is called, Motion Desk. And Motion Desk is used to visualize vehicle dynamics, right? And engineers looking at the plots, and the engineer directly knows, yes, I know what happened there. But as a manager, you might need some kind of 3D visualization or something to see, well, the car still stays in track, for example. And one of our first customer projects for ADAS systems, for like cameras and radars and something, was together with the company MAN, the truck company. And what they've been using was our Open Scene Graph solution to simulate different driving maneuvers. And they had their real camera sensor in front of the monitor, and they were just recording the monitor to see if the objects like a car are detected and if the system hits the brake. So this is how it looks like, basically, right? Putting the camera in front of a lens, specific lens, and they were just recording the screen, and they were checking if the control unit is doing what it should do, right? And from there on, of course, we had new requests, right? So this is like our open scene graph solution, and our customer said, well, we need higher visual quality. And we did like an evaluation of different gaming engines and stuff like that. And well, the Unreal Engine has won. So we developed a new solution, especially for sensor simulation based on the Unreal Engine. This is it. So you can see, I think we did quite well. So this is the same driving maneuver over here, like in two different worlds. Okay, let's get our hands dirty, right? There are different sensors around. I will be speaking about the camera, the radar, and the LiDAR sensor. And I would like to briefly introduce you to the sensor's principles. So for example, the camera simulation, right? How's the camera working? So the camera is a passive sensor, right? So you're having different light sources. You're having headlamps, you're having street lamps, you're having the sun, of course, and the light is reflecting from different objects into your sensor. And for sensor simulation, we have to simulate everything how the real sensor would perceive it, right? So it's not hitting the human eye, it is at first hitting a lens. So the first thing we have to do is we have to simulate the camera lens. And actually there are different kinds of lenses. There is the radial lens distortion. So for example, this over here is a barrel distortion. And it seems like the straight lines are curving outwards over here. So this is one common lens, the barrel. Another one is the percussion. And those radial lens distortions are typically used for a field of view of up to 100 degrees. But there are also use cases where you need a bigger field of view, and those are typically the fisheye sensors, right? So you're having a bigger field of view, typically like 220, with a technical maximum of 360-degree field of view. But I hope you do not need more than 360-degree field of view. It does make sense, hopefully. And of course, you can configure this lens distortion with just a comma-separated value. The next thing you have to simulate when simulating a camera sensor is basically the color, right? Because the way a camera perceives color is that they are putting basically color filters in front of each and every pixel. And this color filter filters out every wavelength except of one. So this means that the actual image doesn't look like an RGB space because it is recorded in like a biofilter, right? In a biofilter, typically you're having like 50% of the whole image in green, and 25% in red and 25% in blue. And afterwards, you are doing some kind of magical tricks to get everything into the RGB color space so we can perceive it with our human eyes. But our customers typically need raw data. And speaking about raw data, it looks somehow like this. So let's zoom in a little bit so you can see that each and every pixel is just one single color. Please excuse me, this is a big fake over here, right? This is a big fake because our monitors, our projectors are in RGB color space. So it is not possible to directly output raw data via a usual monitor. So what I did was just like use Python, import two libraries, write 10 lines of codes to give you an expression how this might look like, right? So because otherwise it would have been just like noise. It would be just noise. But there's also one thing, when you're testing your perception algorithms, you also need ground truth information, right? This means if you're having an algorithm which detects objects, you want to check if each and every object was detected, which was available in simulation. And this is the place where you need ground truth. So what you can see over here is semantic segmentation. This means that for each and every pixel, we can give out the semantic. So you can see, for example, the car over there. The car has a specific color, and the road another, the lane markings have another color. So each and every category has an own color. And on the right-hand side, you can see the instance ID. Because if you're having just the class IDs, and if you're having multiple objects which overlap, this would be like a big, huge monster truck or something. But actually, there are multiple trucks over there. And this is why you typically need the class ID as well as the instance ID. You need both. Another type of ground truth information is 2D bounding boxes. And as you can see in this picture, you can't see anything anymore because there are way too many bounding boxes over there. But this is a great thing. We are in simulation, right? We know the ground truth. We know each and every 3D asset which is placed in our world. So we can create these bounding boxes. But of course, we can also filter them to the objects you need, like cars, pedestrians, and traffic signs. So this over here is simulation. But how is it done on real data? So actually, companies are driving around with a test fleet with different sensors mounted on their cars, and they are recording a bunch load of terabytes of data and petabytes and you name it. And afterwards, they have to hand over the whole data to a specific company, and they're telling them, please label my data. So there are people around dragging those kind of 2D bounding boxes across real data. So there are some AI-assisted ways to create them, but at the end of the day, there is a person who's checking the quality and who is maybe also modifying the bounding boxes. So this process is very expensive for real data, right? And this is the great thing about simulation. You get everything for free, right? Okay, at the end, like a camera use case demo. So this is something we've made with one of our customers from Korea. And what we've done over here is we have been recreating a driving maneuver. So this is actually the digital twin of the 3D environment of the different dynamic objects like cars and pedestrians. And on the right-hand side, you can see our Aurelion simulation. And we just created a camera sensor. We put it into the same position. And over here, those bounding boxes are not ground truth. For now, forget about ground truth, because what we did over here was we injected the camera images into a perception algorithm which detects objects, right? So this is actually an AI-based algorithm which is capable of detecting objects and classifying both. And we just put everything into this algorithm to see how it performs, right? And I personally find this actually quite amazing, I have to admit, because this neural network behind it was trained on real data, not on synthetic data, right? And so there were no modification from our side. This was just like one of our first shots. We just injected the data and it looks quite well. I know this is no scientific approach over here, right? But just to give you a first impression on how our customers are working with our solutions. And of course, again, we are in simulation. So this is so cool because we can do variations. We can simulate it from dusk till dawn. We can enable fog. We can enable snow and rain. And we can change the maneuver afterwards, right? A lot can be done. Okay, from now on, let's leave the camera and go to the non-visible electromagnetic spectrum, to the radar waves. And from here on, radar actually is an abbreviation for radio detection and ranging, right? And you definitely have heard about it. I think it was already used in the Second World War to detect airplanes, for example. But today, it is also integrated in serious vehicles, right? They're on the road, driving around. And did you ever ask yourself how a radar works? Let's have a look at it. So basically, on the right-hand side, you can see our car. Our car has mounted a radar sensor, and it is transmitting electromagnetic waves. Let's call them radar waves, it's easier. And the radar waves are interacting with different objects, and they're reflected back to our radar sensor. And what the radar sensor does, it simply measures the time it takes until the signal gets back, right? We are very close to the speed of light, and you're having the distance, and you're dividing it by 2, and based on this information, you know the distance. And based on the power of your reflection, you, of course, are having some information how good it reflected. And again, a small history lesson over here. Back in 2016, our first solution, again with our open scene graph stuff, was to create a shader-based approach for radar. So what we've done was we took our different 3D objects and we simply put new materials or new textures on them. And within those textures per pixel, there was just like information how good they reflect. So this was like hard-coded, so to say. So this is like our first approach. So on the right-hand side, you can see, for example, the cars on the right. And you can see there are different colors based on the reflection. So this was like our first approach, our very first approach for physics-based sensor simulation for radar. But actually, this is not physics-based because it was more or less a lookup table. This has pros because it's very fast to calculate, but it has also cons because it is simply wrong, right? Why is it wrong? Because the radar also has multipath propagation. And multipath propagation means, when coming back to our example, you could, for example, hit the road, hit the car, and the reflection gets back to you. So this is what is called a multipath reflection. And this is something we cannot do with our shader-based approach. We need ray tracing. And we will see those kind of multipath reflections later on again. So back in 2017, we had a first prototype for our ray tracing approach for radar simulation. And this is something you can call physics-based, right? So you can see in the middle is our ego vehicle. It has like 3 sensors on it, and you can see that it shoots out rays to different objects. So those wireframes are trucks, vehicles, traffic signs, and we only display those rays which also reflected back to our sensor, right? So this was actually a huge, very huge achievement for us, getting this to run. And this also in real time. This was not imaginable 5 years before. When speaking about physics-based sensor simulation, actually the radar is quite complex. Oh, God. So for example, you're having microdopplers, right? And microdopplers means you're having an object. Well, this object could be this guy over there. So there's no Unreal Engine presentation without the Unreal Engine mannequin. So here it is, finally. And you can see in a second that it will move. So the body, the whole body, has a specific velocity, right? And the velocity is mainly green. And when a person moves also his limbs, right? And the limbs are having another velocity compared to the rest of the body. So you can see that the arms are somewhere around red and blue, depending on the position, if they are moving to the front or to the back. And this is actually crucial because the microdopplers are used by the different radar companies out there because they can detect pedestrians with the microdopplers, and even cars are also having microdopplers because the car itself moves in one direction and it has wheels which are also rotating, right? And this also creates this microdoppler effect. And actually, this was pretty hard for us, right? Because you're having this skeletal mesh over there, and the skeletal mesh is moving. You're having updates to the position, and we have to synchronize this to our ray tracing. And this actually costs time and was not that easy to implement. Okay, let's have a look at the use case, right? So this is a truck, and we are simulating the whole vehicle dynamics for the truck as well as for the trailer. And you put a radar sensor in front of it. And right behind the curve there's a bus which has stopped for some reason. And on the left-hand side, you can see a low friction. So it is like the road is wet. On the right-hand side, it is dry, right? So this is simulation. You can change everything, right? And you can see that based on the radar information, it saw that there's an object in front of it, and it is not moving anymore, right? And based on this information, the truck was able to hit the brakes, and you can simulate this on the wet road and the dry road, and the emergency vehicle is already there, just right in time, but no need for it. There was no crash. Okay, a LiDAR simulation. One more sensor, but this one is comparable to the radar, to some extent at least. So to break it down, actually there are different ways on how a LiDAR sensor might work, but let's keep it simple for now. There are sensors around, typically, which again are measuring the time of flight. So instead of transmitting those radar waves, which are having like 77 gigahertz, they are in a wavelength of 905 nanometers, which is like near-infrared light. And the cool thing for the LiDAR is that they're having a great density of information compared to a radar system, for example. So you can see over here, we just put a LiDAR on top of this car, of this blue car over there, and the point cloud over there is the output of the LiDAR sensor. And for each and every point within this point cloud, we're having information like the distance and the reflectivity. So this is the output a typical LiDAR sensor hands out. But we are in simulation. We have far more information, like what kind of object was hit, what category ID is this. Again, ground truth information, right? Okay, again, a little bit of history. This was back in 2018, our first ray tracing for LiDAR. And as you can see on the left-hand side, there are not that many colors, right? So the last image was like colorful. So where do those colors come from? I mean, our goal for sensor simulation is to get as close as possible to reality. So this means if you're looking at this one over here, so this is a quite new image from Aurelion actually, you can see, you can distinguish between the asphalt and the lane markings, but especially if you're zooming in a little, you can see that the license plate, for example, has a way brighter color. So a license plate is actually a retroreflector which reflects the whole light back. So you need this kind of information within your 3D assets because LiDAR and radar do not behave like camera, right? So you cannot reuse the materials from the camera for the radar and LiDAR simulation. So this is why we came up with a new solution. So what we did basically was just to add a new texture to each and every of our assets. So it's basically within the material. And as you can see over here, for each and every pixel on a 3D asset, you can define what kind of material this is. And actually, we are not saving any kind of material properties in there. We're just storing what kind of material this is. And this has the advantage that we're having just one single texture for each and every sensor, right? We're having the radar, the LiDAR. We will be having the ultrasonic. So this means it's easier for a 3D artist. You're creating one single material. And based on this information, there's a lookup table to see what kind of material is this. Is this car body? Is it car headlamps or something? And from there on, we can retrieve the different properties from our database. Let's have a look how this might look like. I mean, we are having the dSPACE sensor car, and the dSPACE sensor car has mounted cameras and radars and LiDARs and you name it on top of it. And we are recording data. We are driving around, we are recording data. And here and there we check this data to see what happens for the LiDAR, for the camera. And over here we can see the camera image of it. And the Audi on the left-hand side is a highly specular object. So this means when the LiDAR hits this object, we are having more or less like a mirror effect, right? So the incoming angle is equal to the outgoing angle. And we are having a retroreflective sign over there. Retroreflective sign means every single ray will directly be reflected back into the same direction. So this is how the LiDAR, the real LiDAR point cloud looks like. And just a few minutes ago, within the radar session over here, I was speaking about a ghost target. And over here, we can spot a ghost. And the ghost is on the top left, the ghost target of a sign, right? Because we are hitting the highly specular object, then the retroreflective sign, you can see how it burns in the point cloud, right? And it comes back. The ray comes back to the Audi, comes back to our sensor, but the LiDAR sensor itself is not capable of checking that this was a multipath propagation. It doesn't know. It simply sees out of this direction, with a specific time of flight, comes a signal. And this is why you can see the ghost target over there. And of course, this is an issue because ghost targets can happen like everywhere. So you are seeing objects which are not there in reality. And what we did was to make a small experiment, right? Just a very small experiment. We didn't recreate the whole environment. We just have this road. We're having our sensors, the specular object, not an Audi anymore, and the retroreflective sign. And we checked the point cloud, and it worked, right? So you can see the ghost target on the left. You can see that the amount of points is reduced. There are some due to transmission of glass. So the LiDAR hits the glass, but there's a transmission. You can hit points behind it. And you can see, again, the ghost target over there. Again, this is no scientific proof, but you can see with the human eye what we are up to, so to say. Last slide for the LiDAR, a use case demo. So we are having a partner. One of our partners is the company Velodyne. Velodyne is creating LiDAR sensors, and they are also developing software for perception. So basically, they're taking a point cloud, and they are trying to detect objects just with the point cloud data. And what we did was to create a specific sensor model in Aurelion, which is just like a copy of the real one, right? And afterwards, the output of our point cloud was injected into their algorithms. And the cool thing, it is capable of detecting cars and pedestrians. And again, there was like not much we had to polish there, right? We were just recreating this model. We could inject it over there, and it worked. And again, this was amazing to all of us. Okay, our hands got dirty. Camera, radar, LiDAR, enough from the physics. Let's speak a little bit about the cloud, because we need actually the cloud for autonomous driving. And when coming back to the challenges in the development of autonomous driving, there are different risks, right? So there are risks that we know, and there are known safe states. Nothing will happen when we will be driving in this kind of scenario. There are also known risks to us. So for example, there's a cut-in maneuver with specific velocities on a highway, and we know this can be a risk, and we know that we have to test those. There are unknown safe states. We can avoid them. We do not care about those states. But there's actually one big issue: unknown risks, right? When speaking about autonomous driving, we are having like critical corner cases, and critical corner cases will happen, and they already happen to all of us when you are driving, right? And they will also happen to autonomous driving. And this is an issue. There are challenges around, and you do not know that those challenges exist. This could look like this. So again, this is like our Korea scene. At the top left, you can see the original scene. We brought this into simulation. This looks a little bit slow, but nevertheless, we are just having different parameters, and we can check if there are any kind of risk, if there's any kind of critical scenario when changing the velocity of our ego vehicle, right? So we changed the velocity to 15 kilometers per hour, and afterwards to 20 kilometers per hour. And based on the simulation, we of course can retrieve, well, there was a crash. And when there's a crash, we of course know this can be a critical scenario at the end of the day. So yeah, and together with the cloud, we are capable of doing like hundreds of execution in parallel, right? So our customers needed a solution to give a specific range for parameters like the ego velocity, and this is why we developed Simfera. And Simfera is a cloud-based solution where you can specify your different test cases, and it will automatically distribute this for you in the cloud. It will do the simulation for you, and afterwards you will get like the test results, right? And you can spot from there on if there's anything, well, which is critical. Okay, two more things. One thing is creating a digital twin. I mean, we've been speaking today about digital twins, about satellite data and stuff like that. We are doing something similar, but we are not using satellite data over here. So our customers typically are having a test fleet with their sensors on top of it. They are recording this data, and they can provide us this data. And typically, this is camera data and LiDAR data. And based on this information, we can create labels, right? Labels for the whole environment, for the road. And from there on, we can create 3D objects, right? To recreate a 3D scene. You can still see the original scene at the bottom right. The next part is to create sensor-specific materials for it, right? We need materials for camera, for radar, for LiDAR. And we have to extract, basically, the driving maneuver to copy it, right? And we are having a process for this, which we can offer, so our customers are able to recreate a real driving maneuver, and from there on, they can, again, do those kind of variation stuff in simulation. To give you a small outlook, what we are working on. So this is like Aurelion today. And currently, we are, of course, checking how to migrate to Unreal Engine 5. And as you can see, this is ray tracing over here because within the car, there are reflections from the house, which is currently not seen. So currently, we are using screen space reflections, right? So this is why you cannot see any kind of house in the car at the top, but over there you can, right? I mean, my car wouldn't reflect like that. It's typically not that, well, great looking. Yeah, but here it looks great. Yeah, this again, our current solution and a first glimpse of how this looks in Unreal Engine 5. I really like it. Especially in this image, for some reasons that I feel like this has some kind of flow. There are some hard corners around the door in our current solution, and everything seems to be somehow smoother, I feel. And one more thing over here, when being at the gas station, we had our problems because light is actually a big challenge, right? We have to get the lighting correct and physically correct. So whenever we were using emissive materials in Unreal Engine 4, they were not well suited for being physically correct. But with the Unreal Engine 5, they do reflect, finally, and this helps us. I mean, you can see how dark the image was like in Unreal Engine 4 and how great it looks in Unreal Engine 5. So we are still working on it to migrate it to the Unreal Engine 5. There are some specific obstacles for us because like the fisheye sensor, basically we are stitching multiple sensors, multiple camera sensors into one single sensor, and we have to check how this works out. But again, this is like a first glimpse for the Unreal Engine 5. Okay, just a small summary, and we are through. Yeah, you just learned today, if you didn't know before, there are 5 different levels of autonomous driving. And the next time your brother-in-law comes to you and he tells you, hey, I got this new car which is like magically driving itself. You have to check it out. The future is now. You can tell them no. This is level 2. You are liable, not the car is liable. You are liable and responsible for it. But again, we will go to level 3 soon. Well, one of the key challenges for autonomous driving are sensors, right? And we as dSPACE, we are providing a solution called Aurelion to tackle this challenge. We can generate sensor data, physics-based sensor data in real time, well, to solve this kind of challenge. Yeah, thank you for listening.